Hello everyone, welcome to the lecture 12 of COMSOL Multiphysics training course. Today we are going to model triboelectric nanogenerators in COMSOL. In this video we do one model and then we continue on that in the future videos. So let's begin. So what is triboelectric nanogenerator or TNG? TNG is a novel technology for conversion of mechanical energy to electrical energy. In fact, the TNG is based on the contact electrification of two dissimilar materials and then electrostatic induction. The TNG is relatively new and it has been applied for different types of applications such as energy harvesting for low power electronics and sensing applications. The TNG has a very high voltage output but a very low current output, and the intrinsic impedance is super high. The TNG may need a circuit design for practical applications as well. So let's see how TNG works. This is the example of a TNG which is based on the contact and separation of two materials. As you can see, we have two dissimilar materials, and when they are brought into contact, because of the triboelectricity, the charges are generated on the surfaces. One surface get negative charges and the other surface get positive charges, depending on the polarity of their materials. And as they get separated, due to the change of the electric field, an imbalance is occurred on the backing electrodes, which causes the charge flow, and this means the electricity generation. I don't want to go through the details. You can find more information about the TNG on internet. So let's see what are the working modes and output characteristics of the TNG. TNG can work in 4 different modes. The first one is the contact and separation mode, which I explained before, which is based on the contact of two dissimilar materials and then the separation of that, and this means that the contact and separation can generate a signal. The other mode is called sliding, which means that the sliding of two different materials may cause charge generation and then electricity generation. The next one is called single electrode, where one of the materials is connected to a reference electrode and the charge is transferred from the reference to the electrode. And finally, the freestanding mode, where a material is moving freely between the two electrodes. Each of them has different applications and advantages. And remember, to make a TNG, at least one of the materials should be an insulator to keep the charge on the surfaces. What are the main output characteristics of the TNG? The first one is the open circuit voltage, which is the voltage where the system is under open circuit condition. What does that mean? Imagine that the load is located between the two electrodes of the TNG and it is a resistive load. And when the resistance is infinity or super large, we can call the open circuit condition. The other important output characteristics is the transfer charge under short circuit condition, which means that R is 0. Remember, we are gonna use them in the future. There are some notes that we need to know about the TNG. First is, if we know the VOC and QSC, we may be able to calculate other output of the system, such as current, power, output voltage, and so on. Also, the interesting thing is we can estimate the open circuit and short circuit by COMSOL simulation, and we will see how we can do that. Also, based on the COMSOL simulation, we can design and optimize and find the performance of the TNG systems. That's why it is very important to know how to model the TNG in COMSOL and how to extract VOC and QSC. Okay, before we continue to our model, I need to give you some important considerations. The first thing is the selection of material is very important for the TNG design. In fact, the materials should be very different in terms of their tribopolarity, which means that the selected materials should have very negative tribopolarity and very positive tribopolarity. So when they are in contact to each other, a huge amount of charge should be generated. So that's why in the design of the TNGs, the materials are selected from the bottom of this graph and the top of this graph. In fact, one of the materials should be selected from the bottom of this series and the other one from the top of this series, so that their contact generates more charge. Okay? The other important consideration is the surface properties of the contact materials. As it sounds, TNG is based on the tribology and the charge generated on the surface. So there are some methods to improve the output of the TNG. For example, if we can improve the morphology and the contact area by adding micro or nano structure or even with chemical functionalization. And finally, the structural design is very important. Depending on the mode of operation, you can have specific designs to effectively transfer the mechanical energy to the system to convert to the electrical energy, right? And there are so many designs for this application. In today's model, we are going to study one of the most important working modes of the TNG, which is called the sliding mode. As it sounds, the sliding mode is based on the sliding of two dissimilar materials. For example, imagine we have nylon with positive electron affinity and PTFE or Teflon as negative affinity. So when they are in contact, the charges are generated in positive and negative fashions, and as they get separated, electrons are transferred between the backing electrodes. And this is a cycle of working operation. And as it sounds, the TNG has an alternating output because the mechanical load should be alternating as well. So let's see how we can model a sliding mode TNG. For this model, this is the parameters that we are going to consider. We have two dielectrics. One of them has positive affinity and the other one has negative affinity. And we suppose that a charge density of 7 microcoulombs per meter squared is generated after they are in contact. In fact, it is a standard assumption. In reality, it may not be a constant value and it may degrade over time, but ideally, we can suppose that a charge density is generated and remain on the surface after the contact of the two materials. Remember, like I said, at least one of the materials should be a dielectric or an insulator. We can also have one dielectric and one metal for the contact of the two surfaces. So metal dielectric is another configuration for the TNG. Okay? So we are going to see if we can get these results. As you see, when the two surfaces are separated, and in fact the layers are very thin, so you don't see the two surfaces. But as the distance x is increasing, for example from 1 centimeter 5 centimeter and maximum to 10 centimeters, we have this potential distribution in the system. Also, we are going to see if we can find the variation of open circuit voltage versus X, as you see in this graph, and also the charge generated in the short circuit condition. So we are going to find these three results: the potential distribution under open circuit condition, the open circuit voltage as X increases, and the short circuit as X increases. So let's begin and see if we can model that. If you want to find more information about this example, you can find it on this reference. Let's do it.
Si quieres vender online, asegúrate de llamar la atención. Ve a Wix e-commerce y crea una tienda.
Okay, so we start with the model wizards, and then here we are going to have a 2D model because of the symmetry and the thin film layers that we have in our model. So I click on 2D, and then remember, for the triboelectric system we need to use the electrostatics. So we use electrostatics, then add, and then continue to the study. For the study we can use time dependent or stationary. The stationary is simpler and we cannot catch the effect of time for sure. For today, let's use the stationary. But in the case that the motion and the speed of motion is important, you need to use the time-dependent study, which is in fact important in some studies. But for now, let's continue with the stationary. And done. Now we are in the software. First we start the parameter, and then we define the x, which is the distance of sliding. For now, I want to start x at very small number. I'm not selecting it as 0 because I have a reason for that, and I will explain why. Let me use a very small number like 0.1 millimeter, and then I will tell you why I selected this. And x is our parameter. As you see, it says x is a reserved name, which means that x has been defined as a coordinate, so we cannot use it. And I'm gonna use x1 for example, which is not a big problem. Okay, that's it. Now we go to the geometry. I switch everything to millimeter because I'm dealing with thin layers, and then we start making the geometry. First, I want to make the bottom sliding surface, so I right click and then a rectangle. The width I know is 10 centimeter, so it is 100 millimeters, and the height, as you remember, was 220 micron, so it is 0.2 22, right? And the location, I want to select it as -100 and the height as 0, which is fine, right? So I click on build selected, and this is the first sliding layer. The other one, I can name it as bottom layer. Okay, now we want to make the top layer, so I right click on the bottom and then duplicate, and I use the name top. They have same size, however we have to adjust the distance. For the x, we are going to use -100 plus x1. In fact, x1 is the distance of sliding, and as you see, when we change x1, the top layer goes to the right hand side, right? And for y, we just use 0.22, right? Which means 220 micron above the bottom layer. So if I click on build selected, then I zoom in, I have the two layers placed on top of each other. As you see, x1 was a small number, so we have a tiny gap between them, which is fine. We're gonna use that. Okay, we are not done with the geometries.
Conectar.
As a ground at the inf and the height as 0, which is fine, right? So I click on build selected, and this is the first sliding layer. The other one, I can name it as bottom layer. Okay, now we want to make the top layer, so I right click on the bottom and then duplicate, and I use the name top. They have same size, however we have to adjust the distance. For the x, we are going to use -100 plus x1. In fact, x1 is the distance of sliding, and as you see, when we change x1, the top layer goes to the right hand side, right? And for y, we just use 0.22, right? Which means 220 micron above the bottom layer. So if I click on build selected, and then I zoom in, I have the two layers placed on top of each other. As you see, x1 was a small number, so we have a tiny gap between them, which is fine. We're gonna use that. Okay, we are not done with the geometries. We need to define an air domain surrounding these two layers, because in the triboelectric systems, we need to have an air surrounding the domain and a reference as a ground at the infinity. In fact, we want to define that as a reference potential. How can we make this air and the infinite domain? It is something new that we're gonna do now. We have to right click, we can select a rectangle. We need to use a huge geometry to make sure that we are far from these two layers, right? For the width, we can use 400, and for the height, I can use 200, right? And if I click on build selected, I have this over there, so I have to adjust the X. So I'm gonna use minus 200 and minus 100, right? Then build selected, and as you see, it looks like this. However, we still need to define a layer and an infinite domain. So we go back to layers, and layer 1, we define the thickness, for example 10 millimeters, and then for all sides, right? And then if we click on build selected, we get this. I'm telling you why I define this. After we define that, we are good with the geometry, and then we go form union and then build all. Okay, before we continue to materials, we have to assign these layers at the edge to an infinite domain. In fact, we want to make this at infinity. So I go to definitions, and then I go here and then select infinite element domain, and now I have domains, and then I select the one on the sides. So we select them as infinite domains, which means it is at infinity, right? That's it. Like I said, I want to place a reference ground at the edges as our reference for the voltage calculation. That's why I'm defining this infinity. Okay, so we are all set with the infinite domain, and then we go to materials. In the materials, I need to define 3 materials, right? So I start with air, so I go to add materials from library, and build in, we add air, add to component 1. Now I can close this, so it is assigned to the whole geometry. Then I will go and I will deselect the 2 layers. Then I use the user defined materials for the top and bottom layers. I right click a blank material, I select the bottom one. So as you see, we only need the relative permittivity, and from my reference I know that it is 2. Then I can change this as bottom, and then I can duplicate this one, but I will clear and then select top and change top, and for the permittivity I use 4. In fact, these numbers are from the reference. Okay, so we are all set with the materials. Now we go to electrostatics, and I know that our depth is 0.1. Based on the reference, the depth through the structure is 10 centimeters. Now we have to define the boundary conditions properly, which is very important for the TNG systems. First, we need to define the reference, which is our ground. So remember, ground is very important, and if we don't define it properly, we may get errors. So to define the ground, we want to select the infinite domain. The outer boundary of the infinite domain is selected for the ground, which means that at infinity we have a ground condition, right? That's why we define the infinite domain. So let's select all the boundaries in the outer layer of the infinite domain as the ground, right? Now you can understand the importance of defining the infinite domain. Okay, so we are all set with our ground conditions. Now we have to define the surface charge densities. As you remember, we have one positive polarity and one negative polarity. So we define a surface charge density, and to select the positive and negative, we have to go to our layers, right? As you remember, we define x as a very tiny number so that we can simply select this surface or boundary and then assign the surface charge density. Remember, if x was 0, it was a little bit hard to do that. And this is a very simple method of doing this. You may have other techniques to define the boundary condition for the two layers that are getting separated. I use this one because it's pretty simple, right? And it doesn't change the problem significantly. So for the surface charge density, we suppose that the bottom layer has negative triboelectricity or negative tribopolarity. So we have minus 7e minus 6, right? We have selected this number based on the reference and it is negative, right? Same thing, but with positive value for the other side. Remember, the two sides have similar gaps or similar separations, so we can use same number. But remember, the main important point is to ensure that the charge conservation guaranteed in the system, right? So I right click and then surface charge density, then I select the top layer, and for the surface charge density I use plus 7e minus 6, right? If the gaps were different for the bottom and top layer, you have to calculate in a way that the charge conservation is guaranteed in the system, right? You can imagine what I mean. So imagine that the area under the surface charge density of the top layer and the bottom layers are different. You have to calculate and ensure that the total charge cancel out each other. Also, if it is a metal in contact with the dielectric, for the metals you cannot use the surface charge density. You have to use the floating potential. But again, you need to ensure that the charge conservation is valid for your system. Okay, we will do one example on the metal and dielectric contact in the future cases. Okay, so we are all set with the boundary condition for the two contact layers, and now we have to define the open circuit condition, which is very important. How can we define that? We just right click on electrostatics, and because we don't have electrodes as geometries, we can assign them as boundary conditions. We are going to use floating potential. If you remember from the piezoelectric problems, one simplification is that we assign electrodes as boundary conditions. However, if the thickness is not small, you can define it as a geometry and then define the material and then boundary conditions. But here for simplicity, we just define the electrodes as boundary conditions. And as they are conductive, we can consider them as floating potential assigned to them. Again, it is because we have an open circuit condition. So I select top layer, floating potential. You can also define another floating potential for the bottom layer. As we look into the floating potential condition, we see that the charge is 0, which is the case for the open circuit condition. In fact, for the open circuit condition, the charge is 0, right? So we are all set with assigning the boundary conditions. Now we can continue to mesh. So we go to mesh, and here I'm going to define extremely fine and build all. Again, the mesh is very quick, and then we have to define the study. There is something important in the study. As we are going to change the position of the top layer, moving from the original position to the right hand side, we are going to sweep the geometry. In fact, sweeping the geometry is a little bit tricky than sweeping other parameters. So for this case, it is better to not use the auxiliary sweep in the stationary or a study extension, because it may give you an error and doesn't catch the point. To do this, we have to use a parametric sweep. So we right click on study and then add parametric sweep, and then plus, we already have x1, and now we need to define the range. So as you remember, the range was from 0.1 millimeter, so we can say 0.1, and we can change it every 2 millimeters, so 200 millimeters, because the maximum distance was 10 centimeters and the unit should go to millimeter. I think everything is set with the parameter sweep. We can click on compute and see how the system output is as x1 is increasing and the top layer is sliding over the bottom layer. Let's do that. Okay, the problem is solved. Let's see what we get. The first thing that we want to check in the open circuit condition is the potential distribution and see if we can get the same results as our reference. So this is the final point. If I want to go to the points that we shown in the reference, let's have x as 1 centimeter. So if I click on plot, I get this one. And as we increase x, we may get more potential distribution. Let's go to 5 centimeters and then plot, and we get this. I hope you can remember this from the reference.